Okay. So let's just keep going with this 4-bar linkage. It looks like this. These angles are 50 degrees. We have a couple on this body of 100 Newton meters. I numbered the members 1, 2, 3 like this. And then the joints are A, B, C, D. And the omegas are all 0, which is always welcome. And the masses are all 1 kilogram. And the lengths are all 1/2 meter. And so far I've only drawn 3 bars. This is called a 4-bar linkage. So where's the 4th bar? Yeah. So the Earth is a very massive bar. Why did I write 0.3? That's 0.5. 0.5. And so far what we've done is isolate the 3 members and do the rigid body analysis. And we have the following equations. So from member 1, we have one equation that says negative 0.383 F12X minus 0.321 F12Y minus 0.083 repeating alpha 1 is equal to negative 1.576. And then from member 2, we have 3 more equations. Negative F12X plus F23X minus A2X is equal to 0. And then negative F12Y plus F23Y minus A2Y is equal to 9.81. That's equation 3. And then last, 0.25 F12Y plus 0.25 F23 Y minus 0.02083 repeating alpha 2 is equal to 0. That's equation 4. And now we're going on to the rigid body analysis. So we've only done the rigid body analysis of members 1 and 2 so far. So we still have to do it for member 3. And we already decided before class ended that member 3 over here has a fixed point at D. And so the moment of inertia is 1/12 times the mass of 1. times the length of 0.5 plus the parallel axis theorem part, which is 1 times 0.25 squared. And you get a value of 0.083 repeating kilogram meters squared. I always do it as the moment of inertia about the center of mass plus a parallel axis theorem part. But by the way, that always comes out to the same formula. So if you're calculating the moment of inertia of a rectangle or a slender rod about its endpoint, it's just 1/3 times the mass times the length squared, by the way. So this is just 1/3 times the mass times the length squared. Okay, so now we're going to free body diagram. And we have the force on 3/2, which is negative F23 because we've already named F23. We have a weight down of 1 times 9.81. Here we have a reaction force RD. And then we have this couple of 100 Newton meters. Any questions about that? Our about point is the fixed point. So I'll start with RD. Rho vector is 0. The force is RdX, Rdy. Cross product is 0. I guess I'll do the couple. So we don't care about this stuff. That is clockwise. So that's a couple of negative 100. Then the weight force. So this is, the rho vector is the vector from the about point, the red dot, to the center of mass. So that should be negative 0.161, positive 0.192. And the force is 0, negative 9.81. And the cross product is 1.576. And then last is that force negative F23. The rho vector is negative 0.321. Positive 0.383. The force is negative F23x, negative F23y. And so the cross product is 0.321 F23y plus 0.383 F23x. This body has a fixed point. Do we need Newton's second law? No. And so the moment equation says negative 100 plus 1.576 plus 0.383 F23x plus 0.321 F23y is equal to 0.083 repeating times alpha 3. And I'll rearrange this as 0.383 F23X plus 0.321 F23Y minus 0.083 repeating alpha 3 is equal to 98.42. And that's my equation. What do we have? 4 so far. So this is equation 5. And now we'll go to the constraints. You don't ever need to do constraints at fixed points. So we don't need constraints at A or D. We do need constraints at B and C. So let's start with the one at B. Two members join there, members 1 and 2. So we're going to calculate the acceleration at B according to 1, and then calculate it according to 2. This one has a fixed point, so all we need is straight circular motion equation, watermelon equation. So this is equal to alpha cross r plus omega cross quantity omega cross r. All the omegas are 0, so that goes away. Alpha, the vector alpha, is 0, 0, alpha 1. And the r vector, this is the vector from the center of the circular motion to the point we care about, the point B. And so this is negative 0.321, positive 0.3830. And so AB is 0, 0, alpha 1 crossed with 0.321 negative, positive 0.383, 0. And that is negative 0.383 alpha 1, positive negative 0.321 alpha 1, and then 0 for Z. Any questions about the acceleration at B according to member 1? And now we have to do it according to member 2. And this time we have to use relative motion because there's no fixed point for 2. So we're going to say the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass of body 2 plus the acceleration of the center of mass of body 2 relative to the ground. This is our A2, so we already have a name for that. This one is circular motion. And by the way, when you're using this relative motion equation, the subscripts of what you're looking for tell you what the r vector is going to be. Okay, it always tells you what the r vector is going to be. The r vector here is going to be the vector from the center of mass to B. It always works that way. Okay. So the acceleration of B relative to the center of mass is alpha cross R plus omega cross quantity omega cross R. And this goes away because the omegas are 0. Alpha is 0, 0, alpha 2. R is the vector from the center of mass of 2 to B. So that is negative 0.2500. So the acceleration of B relative to the center of mass is 0, 0, alpha 2 crossed with negative 0.2500. And that's 0 for X, negative 0.25 alpha 2 for Y, 0 for Z. Yep.
For relative motion, adding up the different accelerations, we're able to flip, say, V over com if we wanted to attach it to something else, to make it relative to something else. Can we also flip the R vector in a similar way to attach it to other things?
I don't follow. Can you say that again?
Say if we wanted we can flip, say, over com, just com over B.
Okay, yeah, by making it negative. You can do that, yep.
Are we able to do a similar?
Oh, good question. Oh, for the R vector, does that, yeah, I mean, I guess if you use that same notation for the R vector, I don't usually use that subscript notation for the R vector, but you could imagine doing it that way, and it does, yeah, right, yes, that does work, yep. Yep.
I was just thinking about that because you said.
Right, yeah, you're exactly right.
That's what I did wrong. I used the wrong R vector.
Damn it!
Because the center of mass, I thought it was going to be 0.
Yeah,
That's why.
okay. Okay, well, right. Yeah, just one little mistake like that and the whole system doesn't solve. Okay, so, well, then the acceleration of B relative to the ground is this plus A2. So we have A2x and then negative 0.25 alpha 2 plus A2y and then 0. And so finally, our equation 6 says negative 0.383 alpha 1 minus A2x is equal to 0. We're just setting these two accelerations equal to each other. That's our equation 6 star. And then negative 0.321 minus 0.25 alpha 2, no, plus, because I'm moving it to the other side, plus 0.25 alpha 2 minus A2y is equal to 0. That's my equation 7 star. Yes?
If you make equation 6 just all positive, that doesn't change the...
No, right, you can totally do that. Yeah, I don't know. I do that a lot of times too. I don't know why. For some reason, it seems to be more visually appealing to have all positives than all negatives. Yeah, you can always do that. Any other questions about that pair of constraint equations? And now, with the 4-bar linkage, we have another pin joint. So we have to go to the constraint at C. And the pin joint C connects member 2 and member 3. So I'm going to start with member 2. Two doesn't have a fixed point, so the acceleration at C relative to the ground is equal to the acceleration at C relative to the center of mass of body 2, plus the acceleration of the center of mass of body 2 relative to the ground. And this is our A2. And this is the watermelon equation. The acceleration of C relative to the center of mass is, well, it works pretty similarly to the last one we just did. We just have a different R vector. So I'm just going to plug that in here. So we have 0, 0, alpha 2 crossed with positive 0.25, 0, 0. Plus that the omega terms go away. And this is 0 for x, positive 0.25 alpha 2 for y, and 0 for z. And so the acceleration of C relative to the ground is a2x, then positive 0.25 alpha 2 plus a2 y, and then 0 for z. You always have to get 0 for these z components because this motion is in the plane. When you're doing stuff in the xy plane, the only things that have z components are rotational elements. Okay. And then member 3. This one has a fixed point. So the acceleration of that point C is just equal to, I'm just going to enter this stuff in again. So we got 0, 0, alpha 3 crossed with the vector from the center of circular motion to C. So that's the vector from D to C. And so that's negative 0.321, positive 0.383, 0. And the omega stuff, the centripetal acceleration is all zeros. And this is negative 0.383 alpha 3, negative 0.321 alpha 3, 0. And so our equation 8 says a2x plus 0.383 alpha 3 is equal to 0. And our equation 9 says 0.25 alpha 2 plus a2y plus 0.321 alpha 3 is equal to 0. And the equations that we have, the variables that we have, so we got 9 equations. The variables are F12, F23. Our equations don't have RA or RD, so those don't show up in our count. A2, and then alpha 1, alpha 2, and alpha 3. And so that's 2, 4, 6, 7, 8, 9 variables. Okay. Well, we have them all here. Will everyone just take a minute and solve this with reduced row echelon form, and hopefully at least two of us will get the same answer? So is that the end of this question? No. What I asked for specifically was, what the? Never seen that screen before. Was so like something you could do with a 4-bar linkage is you could be using one of the spots on this thing. Oh, and by the way, what's the interpretation of this? Member 1 and member 3 have negative angular accelerations, which makes sense. You have that clockwise couple that's making everything rotate to the, rotate from left to right. What's the deal with body 2 having 0 angular acceleration? Well, the heights of B and C are the same at every point as this thing rotates. So that bar 2 is staying horizontal through this whole motion because it's a parallelogram. It has to stay parallel with the ground. And so that's why, even though it's moving and the center of mass has an acceleration and everything, the angular acceleration, the change in angle is 0 over time. Okay,
Yeah, wouldn't this be the same thing as like a double wishbone suspension linkage?
I don't know.
Okay.
I have no frickin' idea what that is.
I'm pretty sure it's basically this, so it's just two parallel members.
Okay.
Kind of like a
Yeah.
knuckle.
Yeah, well, it's a 4-bar linkage. Yeah, 4-bar linkages show up in so many different kinds of machines. So it's useful to at least know what it is, know that you can calculate stuff this way. But okay, we want to calculate the acceleration at B. So how are we going to do that? Well, we have two ways we can do it because B is part of two different members. I guess usually the easiest way to do it is to use a member that has a fixed point. And so that would be using member 1. But in this case, I'm going to use member 2 because the angular acceleration is 0. So the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass plus the acceleration of the center of mass relative to the ground. This is our A2. This is the watermelon equation. And the watermelon equation says, we got that alpha 2 is 0. So this is just 0 crossed with R plus omega cross R. This is 0. This is 0. And so the acceleration of B is just equal to A2, which is 86.18 72.23 meters per second squared. And that's obviously, as long as we did the math right, that's the same thing you would get from using member 1 and just using circular motion to get this. But so this point B is accelerating, with the magnitude we figured out kind of up and to the right, which makes sense. Okay, well, that's it for linkages. I don't want to get deep into the next topic. I mean, we have 5 minutes, but The next thing that we are going to talk about is my favorite topic in this class. Linkages is pretty good. This whole class is full of good stuff. This is a like great time in your life. You're going to look back on this and like dynamics was the peak of my life. The next topic is particle kinematics. And particle kinetics too, I guess, eventually. But the particle part is important. Like, notice that we're going all the way back to particles. We're not talking about rigid bodies here. But now we're doing this in rotating coordinate systems. So, notice we're going back to particles. And there are two ways that a coordinate system, so two ways to make a coordinate system, choose a coordinate system that doesn't satisfy, where Newton's laws are not satisfied, okay? So remember, for Newton's laws to hold, you need an inertial coordinate system. And so what does that mean? There are two requirements for a coordinate system to be inertial. Anyone remember what they are?
Not accelerating and not rotating.
Perfect. So that means the origin is not accelerating. And the axes are not changing orientation in time, so not rotating. If the origin is accelerating, so how would you deal with that mathematically? How would you, yes, yay, you guys are killing it. If the origin is accelerating, you deal with that using relative motion. And now we're going to talk about how to deal with axes that are changing orientation in time. And I want to show you one video before we go. Deal with axes changing their orientation in time. Okay, so what happens if you have a non-inertial coordinate system? Oh my God, I just broke my frickin' pencil. It's lasted me so many years. Wonder if it still works. It seems to. I really don't know. I don't know how it does its thing. I don't know that either. It seems to, I mean, it does have a spot, but I don't know if that's a calibration thing or a charging thing. I think it might just be a calibration thing. anyways, okay. I'll worry about that later.